on the basis of this quantum groups theory, and we have more audience who got interested in this particular area. Over to you, Junaid.
Okay, thank you very much, everyone, and special thanks to the honorable organizers for giving me this opportunity to speak. So, first of all, can you hear me, everyone? Professor Ferezi, can you hear me?
Yes,
This
I
is the
can. I can very well.
Okay, welcome. So, okay, that title of the talk is very general. So, the idea is to just give you some basic ideas what a quantum group is, and then maybe we will see one of the use of quantum groups. And at the end, I will try to present something which I am working nowadays. So, okay, let's see where we go. So, the okay, I think I should go here for some time because the first of all, I have to introduce you the terminology. Why we call them quantum groups? So the point is, uh, in physics we have two type of, I mean, mechanics. The one which we use in our daily life is classical mechanics, and then if you go to the very small scales, you observe something which is not very much like in the classical mechanics. You get something very different, which is called quantum mechanics. Now, if you look at the classical mechanics, your phase space is actually a symplectic manifold. And then your observables are just the smooth functions f on your manifold, and the dynamics of your system is given by Hamilton equation. On the other hand, if you look at the quantum mechanics, the things are a bit different. So here we have projectivization of a Hilbert space, and the observables, they are given by self-adjoint operators. On it, and the dynamics is covered by Schrodinger. So now, the point is, both of these things are mechanics. One is for our daily life, the other one is at very small scales. So the idea is, can we set up one mathematical formalism where you can study both of them, right? So we need a map from classical mechanics, I mean the space of observables in classical mechanics, to the space of observables in quantum mechanics, which respects the structure on both sides. So we need such a nice map. But the problem here is that such a nice map doesn't exist in general. So it doesn't always exist. So to deal with this, there is something called deformation quantization in physics, where you replace your algebra of smooth functions on your classical system together with non-commutative algebra, which is very similar to this thing, but you just deform the product a bit. And that is called Moyal star product. And then the problem is a bit resolved. So the point is, so after this idea in quantum physics, the mathematicians, they try to build a complete mathematical, I mean, field which was named as non-commutative geometry. So it was a very shining area of mathematics, especially in the last 2 decades of the last century. So let me start with this quotation by Dirac, who says, quantum mechanics requires the introduction into the physical theory of a vast new domain of pure mathematics, the whole domain connected with non-commutative multiplication. This coming on top of the introduction of new geometries by the theory of relativity indicates a trend which we may expect to continue. We may expect that in future further big domains of pure mathematics will have to be brought in to deal with the advances in fundamental physics. So after this idea of deformation quantization, we got a complete big field of mathematics which is called non-commutative geometry. So the idea of non-commutative geometry is mainly you actually deform your classical objects to something else, but at some limit you actually recover your classical mathematics. So what we are going to see today is actually something which is the deformation of your notion of groups. And these are called Hopf algebras. So actually Hopf algebras was first time the Hopf algebras was appeared in algebraic topology basically, but then I mean they appeared at many different places. What we are going to see today, we will see them as some kind of a generalization of our group. Okay, let me start with this. So, what is an algebra? So for me, an algebra is actually a triplet where I have a vector space, I have a multiplication, and I have a map which I call unit. And then I want my algebra to be associative and unital. So I want these two diagrams to commute. And if you look at these are just, for example, this one, it is telling you that if first of all you have to, I mean, multiply the first two legs, and then you have to multiply the last one, and here you have to first you multiply the last two legs, and then you have to multiply the first leg. So this is telling you the associative property of the product. Similarly, from these two you can conclude that this is equivalent to the existence of a unit element in your algebra. Why I am doing it like this? Because I want to define another object, a dual object to the notion of algebra, which is called a co-algebra. And the idea is very simple. What we have to do is we just reverse all the arrows in this diagram. Okay? So here is it. So we have a co-algebra, it is again a vector space, but now we have a map from C to C tensor C. Now it is on the other direction, and similarly we have something which we call co-unit. And now we want this diagram to commute and this diagram to commute. And the commutativity of this diagram is actually called the co-associativity of this co-product. And this is actually the co-unit condition. For this epsilon to be co-unit, we need this diagram to commute. These are just the previous diagrams. We just reverse all the arrows. Okay. Now, okay, so then you can define everything that you can define for algebra. You can similarly define co-algebra morphism just by reversing all the arrows in this diagram. So if you have two co-algebras, then a co-algebra morphism is just a map, a linear map, such that the following diagram concludes. And similarly, we say that a co-algebra is co-commutative if it satisfies these things. So if you first apply the co-product, or if you first apply the co-product and then you flip it, it should be the same thing. So it is the covariant of the commutativity. And then a sub-coalgebra is just a subspace of your coalgebra is such that if you take the co-product, it sits inside itself. And similarly, you can define the notion of co-ideal. I don't see it. But anyway, so similarly, we can define co-modules by reversing all the arrows. Okay. Now, if we have once again. Slide. Anyway, don't worry about these. I mean, abstract things. You are seeing many. I mean, commutative diagrams, but it will be very clear at the end. I mean, at the end of this topic, that you will see that it is really connected to the notion of groups. So don't worry. Now, by algebra, this is a vector space which have both algebra and co-algebra structure. So you have a product and you have a co-product and a co-unit, such that your co-multiplication and co-unit, they are algebra morphisms. And if you, I mean, if you put this condition, then automatically the multiplication and the unit, they are going to be co-algebra morphism. And bi-algebra morphism is a linear map which is both algebra and co-algebra morphism. And here is an example. For example, if you take your algebra of polynomials on n by n matrices, then you know that this is a polynomial algebra, the usual product, and then you have the unit element. But then you can turn it into a bi-algebra where you define the co-product and co-unit like this. It is just, if you look at it, it is just the matrix multiplication, right? And it will come later. Okay, now I am ready to define what a Hopf algebra is. So we saw at the beginning we have algebra, but then we reverse all the arrows, we define something with what we call a co-algebra. And then if something have both of these structures, we call them a bi-algebra. And then if together with bi-algebra, we have a map, linear map S from A to itself, which we call antipode, such that the following diagram commutes. Then we say that we have actually a Hopf algebra. Okay, so a Hopf algebra has both the algebra structure, a co-algebra structure, and a map F, which we call antipode, and this diagram commutes. Okay, now let us see. Let us try to visualize this thing a bit. Now you see, we have this theorem that if we have a bi-algebra such that an antipode exists, then it is unique. The antipode of a Hopf algebra is actually an algebra antimorphism. So it means S of AB is going to be S of B times S of A for all AB, and S of 1 is going to be equal to 1. And the last thing is, if a Hopf algebra is commutative or co-commutative, then S square is going to be equal to identity. Can you see where does, I think every one of us has seen these type of axioms for something which we saw in our undergrad course. Yes, it is like a homomorphism, but it is something more. No, it is not actually homomorphism, it is antinomorphism. Yes. So, okay, it is like inverse map in the group, right? So if you know, if you have a group, then the inverse is unique. If this is something like which we call Sawtooth property, that if AB inverse is equal to B inverse A inverse, and then you know that S square is equal to identity. If you take inverse and then you take again the inverse, you go back to the same thing. So this is something actually which is capturing the notion of inverse in a group, and now we are going to see this thing. Okay, let G be a finite group, and by of G I mean the set of all complex valued functions on G. Now together with pointwise operation, this turns into a algebra, right? It is just a very simple thing. Am I using somewhere that it is my set G is a group? No. Here I'm not using the group structure, right? So to capture the group structure inside this this set, which is actually an algebra now, I have to insert the Hopf algebra structure here. So together with this co-product, co-unit, and this inverse. This is what we was looking at before, right? And this is actually the co-unit of F is gonna be F of the identity. And similarly, the co-product of an F is gonna it will take two elements from your group, and it will send it to F of G times G prime. So here you are exactly capturing the group structure, right? Here you are taking a group product. Here you are using the identity, and here you are actually using the inverse. So now from this, you can see that if you have any finite group, you can construct a Hopf algebra out of it, and you are actually using all of the things inside your group. Actually, there is something more to this statement. The category of affine algebraic groups is anti-equivalent to the category of commutative Hopf algebras. So this is a big thing. So can anyone see where am I using that my group is finite? So here I am using here that my group is finite because I am actually I am identifying of G as a width of G width of G times. So this is not always true, right? For finite groups, it is the case. But yes, if you have a finite algebraic groups, then this still holds. So I mean, the construction is same, but I mean, then you also have the reverse functor, and this is like the category of a final. So it means that if you want to study a final algebraic groups, you can just study commutative Hopf algebras and vice versa. But we are not interested, I mean, in commutative Hopf algebras because groups are more easier to deal with, right? So what we want is actually, we want to go towards a generalization of group, which we will call quantum group. So it will be somehow a deformation of our classical groups in this Hopf algebraic language. They are not. Sorry.
What do you mean by anti-equivalent?
So it is, I mean, for any category, you have the opposite category, right? So it is the same thing, but I mean, now you have to take the functor from your category to the opposite category.
Contravariant? Covariant or contravariant? So what is the equivalence of the category in this particular set?
So equivalence of category means that you have one functor from one to the other, and then from the other one to the backwards, and then if you compose them, you get the identity, and that's it.
And where anti-equivalent?
Anti-equivalent comes when sometimes I mean so the composition sometimes you have for while studying category field sometimes you have to reverse the order.
Oh.
Yeah, so the opposite means just you have to reverse the order, and that's it. Okay, so now for example, now this is CSLN, this is a Hopf algebra, again this is a commutative, but now you see SLN is not a finite group, right? It is an affine algebraic group. So you can build the same thing here. So this is a Hopf algebra together with this co-product which we already saw before for the algebra of for the bialgebra of matrices. So this is the same thing, and then you can, because now we are working in SLN, so you can define as here the antipode. This is exactly the, if you look at it, it is just the ijth entry of the inverse, right? It is, so if I write uij's inside my matrix A, so the S of uij is just the ijth entry of the inverse sum. Okay. Now the idea of Greenfeld is to quantize a Hopf algebra by deforming it to a non-commutative Hopf algebra. So such a deformed Hopf algebra is known as quantum group. Okay, so now we are going because for every group you are always going to get a commutative Hopf algebra. But in non-commutative geometry, your symmetries are captured by some non-commutative things, and we are somehow going to see a baby example. For example, this is something called quantum plane. So in general, for example, if you have a fine plane, then you know that for A2 you have this algebra of polynomials. So K of xy, this is for A2 you get these things. But what we are going to do now is we are putting this relation, a Q commutation relation, where Q is just let's say a complex number. So you are slightly deforming your product. Okay, so we call this space, which is actually I mean the algebra generated by two variables with subject to the following relation. We call it a quantum plane. Now similar to the classical setting, if you try to transform your vectors xy and xy via a matrix, what we do in that classical case, then you will see that the new coordinates, they are going to satisfy this two commutation relation if and only if these things hold. And now you see, these are not, commutative relations. These are non-commutative relations, especially this one, right? As soon as you fix q is equal to 1, you are going to your affine plane, right? For q is equal to 1, you are going back to your affine case, but if you have q different than 1, you are getting something non-trivial. But the interesting point here is that together with the same Hopf algebra structure that we saw before here for SLN, it is a Hopf algebra. This one. This is the same Hopf algebra structure, right? But now this is a non-commutative Hopf algebra. So somehow this is not a group, but it is a deformation of a group. That is the reason we call it a quantum group, and for this case we call it the quantum special linear group. Similarly, there are other variants, but I'm not going to define all of them. I will only consider two examples. The first one is this. This is also a baby example. The next one is also a baby example. And this is called Greenfeld-Jimbo quantized enveloping algebra. If you have, actually this construction works for every semi-simple, complex semi-simple algebra. But for me, I am just going to talk about SL2. So SL2 is just, classically, these are just all the Lie algebra of 2 by 2 traceless matrices. So this is a three-dimensional algebra. And now, due to this construction by Greenfeld, and actually this is a very powerful construction. This is one of the reasons Greenfeld got the Field Medal in 1990. So these are very beautiful objects. We will see only this example, but they are very beautiful mathematical. So this is going to be algebra generated by these four variables subject to the following relation. If you look at it now, I mean, you cannot put q is equal to 1 here, right? But after some like change of variables, you can see that actually this is a deformation of your SL. And now with this co-product, co-unit and anti-code, this is actually this U2, this is called the quantized enveloping algebra of SL2. This is a Hopf algebra. And why it is important? Because this construction is very near to the classical cases. The point is their representation theory is very similar to the classical. For example, for this SL2, these are all the irreducible representation. So, for example, similar to the classical case, what happens? So, in the classical case, if you have like this E1, E2, and so on, let's say EM, then what H does is actually it sends everything to itself, and then E is actually pushing it to the next one, everyone, and F is actually taking it backward. So this is the classical story. And if you look at it, it is the same thing, right? So for we are replacing H with K because it is something different. So you see, EM is going to be fixed by this weight, and similarly, EM with E, they are going to go to the next one, and with F, they are going to be toward the back one. And these are some quantum numbers, but anyway, they are not important for us. Okay, so these are all the irreducible representations of UKSL2, and any finite dimensional representation is equivalent to one of them. And similar to the classical case, every representation of U2SL2 is actually, you can write it as a direct sum of these representations. So every representation is reducible to these irreducible representations. Okay, that's all about these Hopf algebras. 25 minutes. Okay. Now, I hope you understand some of the notion what a Hopf algebra is. So for us, it is a deformation of our notion of groups.
Junaid, before moving forward, can you build a relationship between the affine geometry and affine algebraic structure and a roadmap, just to give a sense of understanding what additional information we are getting out of this?
a fine algebraic geometry is most of the time a particular case of this generalized geometry where you send your parameter to some particular value.
And I fail to understand the role of projectivization here. In the beginning, you said that in the classical setting,
Mhm.
so you was using the affine space and where state space in this particular quantum topology is a projective Hilbert
Okay,
spaces.
so actually, no, it is not related directly to this, but it is just like, for example, if you when you study quantum physics, then you always normalize your wave function, right?
Mhm.
So this is the reason I just put the projectivization. So you don't consider actually Hilbert space, but you actually consider the projectivization because you always normalize your wave function. So that's the only thing. I mean, I don't think there is a.
And when we are putting this weight cube, so what kind of changes it is going to bring into the geometric structure?
Oh, so the point is, what do you mean by geometry?
So, for instance, because I was trying to understand from the classical perspective, so when we are having the function which is smooth, and in this particular case, you said that they are self-adjoint operators.
So,
And particularly when
so the
you are,
point is geometrically, what do you? Oh, sorry. Of course, this is a question. What do you mean by geometry? But I mean, what I am trying to understand from your question, the geometry is same thing. You are just deforming your algebra of function. Everything that is working on the algebra level, these are there you are getting something new, and we will going to see this here. So ultimately, they are going to affect the geometry as well. You will see. Okay. So now, actually, the idea of non-commutative geometry was to generalize the geometry, where you allow your algebra functions to be non-commutative. But then it turned out that this non-commutative geometry actually helped us to even understand better the classical topology. And this is what we are going to see now. So actually, this is not the work I am doing nowadays. My field is totally different, but because this is a general audience and it is more, I mean, more interesting, so I will explain this. So what is a knot? A knot is actually mathematically an embedding of a circle in R. And I mean, pictorially, you can see it like this. So so what you do is you just take a rope, turn it around in any way you want, and then you join them. This is a knot. And then you also, if for us, we are actually interested in oriented knots or links. So if you have more ropes, if you have more ropes, then you call it a link. For example, these are links, these are knots. So now the question of knot theory is to find invariants of these knots. I mean, we are interested to see if I give you two knots, can you deform one into the other? This is the main question. But this is not an easy question. So what we do is we have some invariants. For example, the simplest invariant is the number of components of a link. For example, this is a link with two components, right? So you can never deform it into a link with three components. So this is the simplest invariant. So if you have some invariant, then it means if for two particular knots, it is giving you two different values, it means they are not equivalent. So instead of directly doing it, you just compute the invariants and try to see if you can conclude that they are not invariant, they are not equivalent. Okay, but the point is, I like braids. So knots are good, but braids are more good. So the point is, they are like these things. So I mean, you can forget about the mathematical definition. What you do is just take this room and I mean put a line here and then take maybe n ropes and then you fix it here and turn it around and then maybe put it somewhere else like this. So these type of things are called braids. And I will come back to the knots. Okay, don't worry. My main aim is to find the invariants of knots, and we will use braids. Okay. what we can do, if we have any two braid diagrams, we can actually compose them, and the composition works like this. So you just put one onto the other, and then you just rescale it. And the condition is that, I mean, both of your braids should have the same number of sections. The other one is, if you have two braid diagrams, you can take the tensor product. You just put them side by side, and this is the tensor product. The set of all braids with n settings turned into a group. This is a very beautiful example of a group, and we call it a braid group. For any n, you can construct a braid group. Okay. Now I am going to give a presentation of this braid group. So we have these generators. So for sigma I mean, when at the ith place I have this type of crossing, and sigma I bar, I mean, where at the ith place I have this type of crossing. Actually, if you look at these, they are inverses of each other, right? If you compose them, you will get the identity. So, for example, now first we have this type of crossing, then we have this type of crossing. Now you see, you can just so they are just the inverses of each other, right? The point is actually these sigma I, they generate this gradient, and we have these relations. So if they are far enough, I mean, if their difference is greater than or equal to 2, then they do not communicate to each other. So this is simple, you can just think it in your mind. And this is something called the braid relation. And this is the Artin's theorem in 1947, that actually this is the presentation of a braid. And these, you can actually draw also this one. So sigma I plus 1, sigma I. So sigma I mean I have to first take this crossing, and then I have to take sigma I plus 1. So I mean I have to take a crossing here. And then I have sigma I again. So here I have this crossing. And now it is telling me that this thing should be equivalent to sigma I plus 1. So now I have to crossing here. And then sigma I, so I have here. And then I have sigma I plus 1 again. See? So now you can actually see that they are, you can just stretch some settings, and then you can turn it around, right? You can go from one to the other. So these are the two relations, and pictorially they look like, the second one looks like this. The first one is very easy. They do not communicate. Now, I actually started from a knot, but then I went to the braid. Why? Because I can always construct a knot out of a braid. So if you give me any braid, I can just take the setting, the end point of the settings and join them. So I can just close everything, and this I am going to get going to get a link, oriented link. And actually, this is the theorem by Alexander, which says that actually you can construct every oriented link using this thing. So every oriented link is actually a closure of some braid. But now the question is, can it happen that you have two different kind of braids, but they give you the same link? It can happen. So we have to also consider this situation. So the first one is this situation. This is the simple one. So if you have sigma and sigma prime, if you compose them and then you join, or if you have sigma prime and sigma and then you join, they are going to give you the same links. And the other one is this one. So now, if you have this type of situation, then, for example, you see this the number of settings in this braid and the number of settings in this braid is different, and they are going to give you the same oriented link. So it means if we want to study braids while studying oriented links, because our original problem is to study oriented links, and we went to study braids. So it means we have to study grades up to these two moves, because we have this theorem by Markov who says that the closure of two grades are equivalent if and only if we have these two things, that either they are equivalent or they are related to each other via a finite sequence of these two moves, M1 and M2. So it means the study of oriented links up to isotopy is equivalent to the study of grades up to Markov. Okay, now why we went from links to grades? Because we saw that to every grade we can actually associate a group structure. And then the point is, to each group, now we can study the representation theory. And from there, we can somehow use algebraic structure to build some invariants. So what we do is that for any finite dimensional vector space V, we define a map rho R, and it works like this. That for every upward arrow in my diagram, for example, like this. So this is an upward arrow. This part is if I consider this part, this is an upward arrow, and this is a positive crossing. This type of crossings I call them positive, and this is an upward arrow. To upward arrow, I just associate the identity map. And to the positive crossing, I associate something R from this endomorphism of B times B. And to negative crossings, I just assign R inverse. And then I actually extend this map R using these two operators. Okay, now for this map rho R to be a representation of my group, it should actually be the compatible with my grade group, right? So it should satisfy these two conditions. The first condition is always true. And the second one, actually this one, if you look directly at this one and you try to see it here, you will end up with this equation. You want this equation. So not for every R you can construct representation of your grade group, but for some special R's, you can actually construct the representation of your grade groups, and that special R should be a solution of this equation. And I think some of you already knew about this equation, and these are known as Yang-Baxter equation.
Okay, what do you mean by plus and minus?
Yes, so plus is crossing of this type, and minus is a crossing of the other type. So they are actually inverse zero.
And we are building this particular structure of looking at the crossings.
Yes. So you take a grade, and then you take your grade group in n setting, and then to each grade you can associate something following these rules, right?
What is the domain of rho R?
So it depends actually on your on n. What it should be. It's gonna be yeah. So it is going to be endomorphism of B times n. So n is the number of settling in your grade group. So because for the upward arrows you are just you are just associating an identity map, and for the crossing you are associating something. Okay, so now we want some solutions to this equation, and the solutions to these equations are called R matrices. And this is a famous equation known as Yang-Baxter equation, because it also actually arises in physics, in statistics and mechanics. This equation arises, and they also call it Yang-Baxter equation. And now the point is why we are talking about all these representations, because if we have any oriented link which is a closure of a grade sigma, and R is an R matrix, and mu is some map from endomorphism of B, such that these two conditions holds. Then this map which associate to each link something, it could be a polynomial or something else. It is actually an invariant of oriented links. So using our theory of representation for grade groups, we can actually construct the invariants of oriented links. But until now, I didn't give you any R matrix, right? So the question is, do these R matrices really exist or not, right? And the answer is, because my talk is about quantum groups, the quantum groups plays a key role here, and they give you R matrices. There are certain kind of not every Hopf algebra, but there are certain kind of Hopf algebras which we call actually ribbon Hopf algebras, whose representations they actually gives you a systematic way to construct R matrices. Once you have R matrix, you can construct the invariance of your oriented links. For example, for the case of the two-dimensional representation, which we saw before for U to SL2, you actually recover this celebrated Jones polynomial. Maybe some of you already knew, but I am not going to explain what Jones polynomial is. This is a polynomial to each oriented link. You can actually, following some rules, you can associate this polynomial, but this is very powerful. Actually, again, the Vaughan Jones, he actually received Field Medal in 1990 due to his, work on Jones polynomial and also something else. And also Edward Witten, he shares this Nobel Prize with Jones, and his work was to give a physical meaning of this Jones polynomial in quantum field theory. So this is very powerful invariant, not just for knots, and then you have many more things. But now we don't have only this Jones polynomial. We have many quantum groups which shares the structure of different Hopf algebras. You can build the same theory, you can get R matrices, and you can actually construct a lot more families of invariants. And this is a complete theory which is known as Rishi-Leffen torus invariants. So Hopf algebras, they are not just important, just for generalization purposes. They are also important for your classical low-dimensional topological problems. And in fact, maybe some of you are not interested in oriented links. What is this? You just associating some rope and then you are studying this. No, these are not very weak things. To each oriented link, you can actually do some operations which are called surgery, and then you can build three-dimensional manifolds out of it, oriented three-dimensional manifolds. And the point is, using these quantum invariants of links, you can build the invariance of three-dimensional manifolds. So this is a very powerful theory, which is not just, restricted towards the oriented links. It also works for the invariants of three-dimensional manifold. So, okay. One open problem which still exists about Jones polynomial, and it is very easy. Can you build an oriented link whose Jones polynomial is equal to the Jones polynomial of unknown? So this is actually a famous open problem which still exists for Jones polynomial. Okay, so now I have some few minutes. So let me talk about just a few words about what I am interested in. So not invariants, these are just the interesting things for general audience, but this is the topics I am working on, and I am interested in these things. So it is called the differential calculus. So it is the algebraic version of the exterior derivative. So if you have any algebra B, and then you associate a tuple where this is a B bimodule and D is a map from B to this B bimodule such that it respects Leibniz rule and you have that this is actually a span of this type of things and then you have like this type of connectivity. So classically, I mean this and classically these are the properties of exterior derivative. So I mean you have algebra of smooth functions on your manifold. And then D is actually taking you to the exterior algebra, right? So this is just a generalization because now our algebras which we are now considering, they would be non-commutative. Here, when we are studying classical geometry, every time our algebra of smooth functions, they are commutative. Now we are working in non-commutative geometry, so there could be more options. And the point is to study these differential structures on these type of space. And if we have more structure, I mean, because we are working with Hopf algebras, so we say that a first order differential calculus on a left A co-module algebra is covariant if it respects your co-module structure. So this diagram concludes. So we are interested in actually to give me any Hopf algebra, then we are interested to classify all the differential calculuses that exist on your algebra. And it is not an easy problem and sometimes actually a bad problem. Because sometimes it happens that you do not recover your classical picture out of the quantum. For example, sometimes there are dimension problems. For the classical case, you have exterior algebra of different dimensions, and when you go to the quantum setting, you have exterior algebra of completely different dimension. So what we do is we sometimes study, instead of studying the big algebra, we actually restrict to like the quantum version of homogeneous spaces. So we take the quotient of the bad part and then we try to study the differential calculus on this type of homogeneous spaces. We call them, so these are actually the, like in the classical setting, you have the algebra of invariants. Here we have actually the algebra of co-invariants. And we say that it is actually a quantum homogeneous space if this technical condition holds. So the point is to study differential structures on these type of quantum homogeneous spaces. And an example could be, I mean, what I am studying together with my advisor, we are studying differential structure on something called quantum flag manifold. So you can fit your flag manifolds in this picture, and then we are actually studying differential structure on these quantum flag manifolds. So I know that you will not get anything out of this, but I am just trying to show you that these are the type of things we study. And so we have in the classical, for example, in the classical case, you put Q is equal to 1. You actually you are going to get your exterior algebra. But this is so there are a lot of construction. I mean behind these details, and somehow this is because you can construct a lot more calculuses on your non-commutative space, but this is somehow one of the nicest example, and we compute these, and then we actually study the complex geometry on this full flag manifold, full flag manifold F3, and we, I mean, classify the complex structure. I mean, what you can do is once you have differential structure, then you can study the complex geometry. I mean, the complex structure, the integrable complex structure, and this type of thing. So I am interested in this differential calculus stuff nowadays on quantum homogeneous spaces. So that's all. Now this is bibliography because I talk about many things. So these are the basic things about quantum groups. These are the classical literature by Kessler, by Majid, and by Klimek-Shmutian. And then these two books are about quantum invariants. This is I think this is the best one. And then I mean, if you are interested in physics and you want to see why these quantum groups are interesting for physicists, then you can also look at these books. For example, this is the deformation of Minkowski and conformal superspaces in terms of quantum groups. And this is a very famous deformation of quantum Minkowski space. This is called Kappa-Minkowski. And then one due to Maggi, it is also the Kappa-Minkowski. And then here is the literature for if you want to see something about differential calculus on Hopf algebras. So this is our recent article which I was explaining at the last slide. So thank you very much.
Are there any questions by the audience? It's a pre